Today we are going to start a new chapter, and this is going to be the last chapter in this long semester. We are coming to the last week finally. But this is again chapter 6 is a nice chapter that I like. It's about like it's similar to like we're going to see uh, states and edges between states like a graph. We are going to see graph, but it's not about graph theory. It's about time series, random variables that change over time. Um, by the way, if other sections, probably section 3 is not going to be able to finish the entire chapter 6 until the end of semester. So depending on how chapter 3, section 3 goes, covers these topics, these last two sections, 6.3 and 6.4 may not be included in the final exam. So we are going to make an announcement about that after the semester ends, before the final exam. But definitely all the sections are going to cover sections 6.1 and 6.2. Today we are going to talk about these Markov processes, Markov chains, how things change over time and things like that. But before we start this, I want to finish up chapter 5 for good. Do you have any questions about this assignment we have went over last time? It was towards the end of the lecture, so we didn't. It was a bit of a rush. So if you have any questions that are parts that are not clear, you may also try to run this on Octave Online and see how it goes. First, let me start running a very small simulation of size 100 and see uh, how it will get more accurate as we increase the sample size, and how we can get the idea of how this for loop runs that many times. The original number was 38,416. Okay, so let's run a smaller Monte Carlo simulation with size 100. But let me do a quick reminder of what we did last time. So we have a complicated situation here with in this problem where there are multiple random variables, like the number of fish caught in 3 hours. That number is something random. The fisherman may catch 10 fish, 12 fish, 15 fish, so we don't know, but that's a random variable. And each fish weighs differently, and the weight of the fish is given by this probability density function, which is a piecewise polynomial. And if you Wolfram Alpha has a nice website in which you can enter these piecewise polynomials and see how they look. Okay, there's a nice visualization. Let me try to do that actually. So we can just copy this, and let me see how we were doing piecewise function Wolfram Alpha. So yeah, it's written like this. There's a piecewise, you write it, probably there's an example here too. Yeah, we can actually, there's this plot, copy the clipboard. Let me just copy that and also directly go to wolframalpha.com. All right, so you can write here, you can use this. This is a really nice, very good website, which you can do integrals, derivatives, definite integrals. So plot piecewise. So we write the function, and then we write the variable and its boundaries. For example, the first one here is, it's 0 when x is less than 0. Let's also write that. It's when x is less than 0. Oh, this was something else. So we write it. When x is less than 0, it's 0. Okay, when x is greater than or equal to 0, and we can write here something like this. So 0 greater than or equal to x, and x is until 1. So we write 1 here, and we type our function here. which is 0.4x cubed minus 0.6x squared. So the good thing about this is you can write 0.4x without the multiplication here. So it understands that it's a coefficient of x. So you can write it like this, minus 0.x squared, and there's plus 0.3. So that's my second piece, right? And this tells you where you want to plot. For example, plot it between -2 and 3. Let's plot it between -2 and 5. I want to see the boundaries where it's 0, 2. Okay, now I'm going to just copy this one. Here, I get all the parentheses matching, and the third piece, minus 1.2. Yeah, right, let me write it here. Minus 1.2 x minus 1 cube plus 1.8 x minus 1 squared. By the way, if you notice any typos here, oh yeah, it's not going to be a problem. You can write also, oh yeah, it's going to be a problem. It has to be like this. Sorry, it's a problem. In order to indicate x is between 0 and 1, you need to write it like this. Okay, it's 0 is not. If you write it the other ways, it will be a problem. Yeah, copy and paste. Yeah, I can copy and paste from here actually directly. You're right. So this part, this other part, only the squares will. I will have to use this hat symbol to do that. But other than that, so this one, let me see, 1.2 squared, 0.1, and this is between, x is between, oops, I didn't paste it correctly. Oh, I copied the other part. Let me just copy this one, come here. Yeah, some symbols, you have to write it like this, between 1 and 2. And the last piece, which is this one, let's try to copy it. And let's see what will happen. So the last piece here, again between curly braces. Okay, yeah, it actually messes up instead of all these special characters are messing this up. So I'm actually going to just copy this thing from here, then modify the coefficients. Yeah, it didn't help at all. So let me just, yeah, because of the PDF has these special symbols, that's the reason. So the last part, 1.2 x minus, yeah, modifying is much easier, right? X minus 2 cubed and minus 1.8 x minus 2 squared and plus 0.7, and I have to write here 2 less than or equal to. Actually, this less than or equal to's are okay, I have to put here exactly. I will just, I mean, it doesn't matter, it's a continuous function anyway, but let me just get it exactly the same as the other one. So 2 less than x less than or equal to 3, and then the final piece, which is simply saying that it's 0 when x is greater than 3. Okay, I think that should do it. Let me just copy this in case we have an error. Okay, if you want to try that out, let me also copy it here in the chat box. All right, so when you hit enter, now if there's an error, it will show, or it will try to do some. So it's trying to plot it, compute, interpreting as plot. So yeah, it actually, there was some errors here. That's why it just plotted this one. I think we need to put a space here. Plot piecewise. Oh, and there is a parenthesis missing maybe. No, this is it. So this is okay. Oh, there's, what is, so this is the parentheses for the boundary, where you want to plot this. This is the parenthesis, this should be the parenthesis for the piecewise. part. Let's see. Yeah, it's a long one. Yeah, it's the for the piece was. I think this one is this parenthesis is a problem here. Let's see. Just before that, I need to close another parenthesis. That was a parenthesis mismatch. Yeah, I forgot this one. So there has to be a parenthesis here too. Now let's hit enter. Yeah, look at this. I mean, the way it printed this out, it's really nice. It looks very much like the one in the PDF. I mean, the figure. Let's see. So 0 when x is less than. Yeah, just compare these two things. They are exactly the same. 0.1 between this and that 0.7, 2x, and that's it. So what you can do is you can also try to integrate it. You can get a definite, you can write this piecewise function instead of saying plot in the beginning. You can say integrate from this to this. Oh, actually, maybe the definite integral. Yeah, you can integrate it and see that the area under the curve, as you can see, it starts, this is a strange PDF. It doesn't start at 0. Also, it doesn't end at 0. The zeros are just abruptly. I mean, outside the boundaries, it doesn't look continuous. But within the bounds, it's continuous. All these different piecewise polynomials, they seem to be different functions, but it seems like a continuous curve, right? You're going to see how we do such polynomials in computer graphics class, where we have knots and we combine them with cubics, for example. All of these are cubics, polynomials of degree 3, and they are connected at the junction point, even at 1. When you look at the derivatives at 1 in this curve, they are equal. Okay, if the derivatives of these two polynomials are equal, this gives you the sense that there is no abrupt change at this junction point. So this looks like a single smooth curve that goes on like this. So it's an interesting shape, which tells you probably in the lake there are two different populations of fish, which are maybe very small. Maybe these are babies that was just born, and these are like the adult fish that have like a normal like distribution. So this is the PDF we have. This is how the fish weight looks like. It's actually, this PDF is a little bit doesn't make sense in the sense that catching 0 weight fish seems to have a probability of 0.3, but don't forget that this is the probability density function. This is not PMF. So point probabilities is 0, which means that it doesn't mean that the curve starting at 0.3 does not mean that the probability of catching 0 weight fish is 0.3. This is not true, because the probability of catching 0 weight fish, it's a point probability, and this is a continuous function, it's 0. But what you may say is that the probability of catching very small weight fish, for example, between 0 and this is 1 kilograms, I think. It was kilograms, right? Let's see. In kilograms. So these are big fish in general. So the probability to catch, for example, a fish between 0 and 200 grams is the area under the curve here. Okay, the area under the curve here. Maybe, for example, 0.06. Maybe with 6%, with 0.06 probability, you may catch a fish between 0 and 200 grams. Okay, so this is our probability density function. Now, as you can see, this is an interesting like two-mode function. Doesn't look like a family of distributions that we have seen before. So our goal will be to generate random numbers that follow this probability density function. Maybe a lot of fish with weight 2, but some with weight 1. So any weight within this range is possible. They're all non-zero probabilities. Okay? And this is not the derivative. This is the arc length of the curve, which we're not interested in arc length, the length of this curve. If you're interested in the derivative, the integral, you can also take a look at that and verify that the area under the curve is exactly 1. So how I designed this curve? By using the techniques I learned from computer graphics, I was able to come up with these polynomials. I tried to say, okay, let's have some boundaries at 1 and 2 that have them here. So I played them a little bit so that the area under the curve is 1. Okay, but anyway, so the problem is the number of fish is random, the fish weight is random, two things that are random, and there are many of these variables, many random. If the fishermen catch 11 fish, there will be 11 independent random variables for each of those 11 fish. Okay, and our goal is to estimate the probability that the fisherman is going to catch a fish totaling more than 25 kilograms in 3 hours. This was the Poisson random variable with lambda is equal to 4 is for 1 hour. So in 3 hours it becomes 3 lambda, so lambda becomes 12. All we need to do is try to simulate this situation. First, simulate every fishing session. So a Monte Carlo simulation, this capital N here, refers to the number of simulations that you're going to run. For example, if it's something about a day, you're going to simulate maybe a day. If what you're asked is about a single day. Here, what you're asked is about 3 hours. So we are going to simulate a 3-hour session in a Monte Carlo run, in a single Monte Carlo run. And we are going to run this 38,000 times and do the counting to the 38,000 is going to is needed in order to have, with probability 0.95, in order to have our probability, the final probability that we want to compute, the probability that the total weight is greater, we want to estimate this probability with 0.95 confidence within 0.005 of the actual probability, which we don't know. We don't know the actual probability, so we'll be estimating this. But if you run this 38,416 times at least, you will be able to, with this confidence, you will be within that probability. Okay, so the way we do that is we have our main loop that tells us how many Monte Carlo simulations we run. We first generate the number of fish code by sampling it from Poisson distribution. Now, one thing you may actually, then we have, if you look at this curve on Wolfram alpha, you see that the highest point is attained at 2, x is equal to 2, and it's 0.7. So plotting this curve in Wolfram alpha helps to say that, oh, okay, when I'm doing my rejection sampling, this is my box. I'm going to put a box between 0 and 3, the x coordinates ranges between 0 and 3, and the y coordinates ranges will be between 0 and 0.7, which is the highest point of this curve. It will not be, if you make it between 0.75, it will not make it really bad. I mean, you don't need to be exactly at the top level. Okay, then we are going to sample. This is where rejection sampling occurs. We sample y number of fish here with rejection sampling. The initial coordinate, which we start with, the initial random sampling starts at 0 and m, which may not make sense at all. Why do we start our rejection sampling? So that's like a convention maybe, but it would be perfectly okay if instead of initializing Cx and Cy like this, if you had initialized Cx and Cy like this, because m is known, s is known, t is known. I mean, there's no point in initializing Cx and Cy with 0 and m. Okay, you can, oh, this is not the comment here. The comment is with this. So you could have initialized the initial random point with really some random numbers. Okay, actually, sorry, we need to get u and v random also in order to have u and v, some random numbers here. So we can initialize, what I'm saying is that the initial rejection sampling point could be initialized, so we can randomly at a point here. It doesn't, the initial point seems to be initialized here, which is guaranteed to be rejected. So it guarantees you to go inside the while loop, but you could have, what will happen if your first initial point is here? Accepting that point, is it bad? No. I mean, you won't go into the while loop because you will accept your point the first time, and that's okay. We can accept that point. So what happens in the while loop is this. In the while loop, we keep staying in the while loop as long as the generated points are above this uh, curve. As soon as we find a point under the curve, we exit the while loop and we report this as the weight of the fish. So since we determine whether it's above the curve or below the curve by evaluating this PDF at that x coordinate, we will and reporting that the x coordinate of our random point as the sampled variable. The possibility of exiting the loop will be higher for x values that are here because the PDF has a high value, so you will be more likely to be under the curve. So the generated y values, therefore, is going to be following this PDF. That's the basic idea in rejection sampling. But as I said, the initial value here of 0 and m, if it was confusing for you, you may just initialize your random Cx and Cy again with a random point. That's perfectly fine. It doesn't make your rejection sampling incorrect. Okay, so we could have done it like that. So let's do that. And as I said, as long as the generated points are under the curve, so actually let's take a look at this one. Cy, sorry, when it's under the curve, we accept it. As long as the generated points y coordinate is above the curve, we keep this while loop. Okay, then the generated weight is added to the total weight, so we keep a total weight for that session. For a 3-hour session, we accumulate these weights, so this becomes a single weight of fish caught in a single 3-hour fishing session. Then we accumulate those in our large for loop for n times for all of them, and then we just observe those sessions, see in how many of them were you really above 25 kilograms. So you just use this on your array. It turns into a binary array for which if the total weight for that entry was greater than 25, we get a 1, otherwise we get a 0 for that entry. So the average of those zeros and ones becomes your estimated probability. So it's the ratio of sessions that have more than 25 kilograms, and that's the probability that we're looking for. The total weight array, if you take the average of the total weight array, it becomes your sample mean, and it's the expected weight. So you can also predict the weight of the fish that you catch by just taking the average of your Monte Carlo simulations. The sample standard deviations becomes the standard deviation of your weight. So, and then you can report these. So that's basically a more thorough explanation of what went on. And let's try to run this. I'm going to just copy them in Octave Online. On Octave Online, so Octave Online. And just wondering the probability and how it's going to change. Oh, the Poisson loop, yeah, let me explain the Poisson loop again. So this was, the Poisson loop is actually like this. It starts, so let me, do it here. So the Poisson is a discrete distribution, 0, 1, 2, 3, 4, something like this. Okay, so 12 is the expected value here, 15, it goes on like this all the way to infinity. So when you look at this Poisson distribution, it's going to probably be something like this. I'm not sure. Okay, for lambda is equal to 12. Okay, if you draw your Poisson. But this is not a continuous distribution. So it's a discrete distribution. So it's going to have some discrete probabilities that are like this, the PMF. All right. Now, if you look at these values of the PMF, and if you look at the CDF of Poisson, each of these probabilities are going to occupy certain interval in the CDF from 0 to 1. Okay, so this was about how we sample any arbitrary discrete distribution. So what we do in Poisson is that we generate a uniform random number, a single uniform random number. If you look at the code again, we are not generating uniform random numbers again and again. Inside the loop, we don't generate uniform random numbers like in rejection sampling. We generate it once, okay? So it's the idea basically here is this is the entire probability distribution space for Poisson CDF. The 0, 0, 1 space is divided into probabilities based on how high these PMF functions are. For example, if the probability to have 0 is small, it will have a small interval. The probability of 1, it will have the next interval. The probability of 2, it will have the next interval. And you see, what is the, if I ask you what is the interval of 3, it will be CDF of 3 minus CDF of 2, right? I mean, so this is the CDF of 2 or less, and this is 3 or less. The interval, between CDF of 2 and CDF of 3, we have the interval dedicated for number 3. So what we do is we generate a single uniform random number between 0 and 1, and we try to figure out which interval it belongs to. And the way we do that, which interval belongs to, is that we start asking from the left-hand side. We start asking, is this u within the interval of 0? Is u within the interval of 1? No. If is u within the interval of 2, that's what the loop is. Okay, the loop starts with CDF of 0, checks whether if u is less than CDF of 0, what does it mean? It means that the generated u is within this interval. So you spit out 0 for your Poisson variable. If the generated u, and then ask you, you check whether, oh, is the u CDF of less than 1? So we keep accumulating this CDF, it's here. So here we keep adding. So this is the PMF of Poisson, but as we keep accumulating it, this F actually becomes this current CDF at I, okay? Actually at I plus, at I. So if it is, so this is the next CDF. If it's less than that, we know where the interval is going to be. So the Poisson loop keep accumulating these PMF values to figure out where that U falls. And it does that not like binary search. So it becomes linearly, we search from 0, 1, 2, 3, 4, 5. The thing is that this loop, I mean, this area between 0 and 1 actually is divided into infinite intervals, right? Because Poisson variable go all the way to infinity. But here, the last part of this partition is divided into very, very, very small intervals. So, for example, even if your U value is 0.9999, if you get this as your random variable, it will probably fall into the interval of 18, although, or maybe more than that, but all the way, theoretically it goes all the way to the infinity, the intervals are going to be very, very, very small. So you're bound to, at some point, you're very likely to exit the while loop while you're looking for 18 or 19 or so. But the Poisson loop searches from the beginning. Okay, I hope that's clear. And yeah, let's try to run this on our Octave Online. And we don't need any statistics package because all we have is just some mathematical functions. So let me run it like this. So what is n? N is 100. If you look at what total weight is, it's an array of 100 zeros right now. Okay, so it's an array of 100 zeros. Now I'm going to copy and paste this for loop, which is going to run for 100 times, 100 iterations. Let me copy this. When you hit and it's running, and it's luckily finished in less than 5 seconds. Right now, total weight, if you again take a look at what total weight looks like, total weight is now this. Look at this, very nicely. These are all different fishing sessions. In the first fishing session, he caught 28 kilograms, 27.6 kilograms of fish. Then 16.6. He was unlucky. He was unlucky actually in the next three. Maybe the number of fish he caught was small, or maybe the weights were small, but this is what you get here. These are all very nicely. It's like a game. We are simulating a fisherman catching fish for 3 hours, and this is our random simulation. Sometimes he gets, you can look at what's the maximum amount. Yeah, 37 kilograms. Least amount of, and sometimes 11.9 kilograms, and sometimes 8 kilograms. But now, if we, so this is, when we do it 100 times, your estimation of that probability will be very accurate if you do it for 38,000 times, 38,416. So let's do these two. Oh, this fprintf is also, wow, this is a function fprintf in MATLAB. I didn't know that. So I wrote this code earlier, but yeah, let's see. So estimated probability 0.2. So it's a very, I mean, only the number of, so it was really, there were 20 sessions here, exactly 20 sessions by chance. If we run this again, it will probably be different. And expected weight is this, and the standard deviation was high. Probably because of the sample size, our Monte Carlo simulation size was small. Let's change that. Let's try to run this time 38,416 times. Okay, again, lambdas. Let me initialize them again, and let's see how long it's going to take. So now it's a 38,000 size array, and this loop is going to run for 38,000 times. So therefore, I'm guessing that our Octave Online 5-second limit is not going to be sufficient. So we will need to add seconds to our simulation as it's nearing. So let me see how many times I'll have to click this. But luckily it gives increasing amount of minutes. So, but you have to be really quick. You can only add 15 seconds, so that's something constant. But that link only comes up in the last couple of seconds, so you have to be quick in clicking that. So that's a bad thing about Octave Online. In the last 2 seconds, you have to collect. So what's still running, as you can see, I think it will run in about 1 or 2 minutes. So we will, yeah, it's finished actually. We use Chebyshev inequality. So this 38,000 is computed by using the Chebyshev inequality by Z alpha. We did it by 1.96. So it was like this, 1.96 divided by your epsilon, which was 0.000. Well, how many zeros did I have? 2 zeros. Okay. 0.005, we get this squared, and we multiplied it with our largest variance we can have when we're estimating probabilities. We don't have a guess at our estimate of the fish caught in 3 hours, the probability of fish caught more than 25 kilograms. So we didn't have an estimate for our probability that we want to find. So we assume the worst variance, which is 0.25, which is 0.5 times 0.5, which was p times 1 minus p. Okay, so this is how we figured out that 38,000. So if you do that, yeah, I already have it here. 1.96 divided by 0.05. So that's the equation, and that's 30. No, it was n is equal to 100 was just something that I want to show you to see how it will look like when your sample size is small. Okay, it was just something random. I just wanted it to finish quickly to show you. So it was something arbitrary. Yeah. Now it's finished actually in about a minute. I didn't have to click that much. Let me copy these last 6 lines, and let's see what the probability is within 0.05. So this is the probability. The estimated probability now, I mean, when we performed the experiment 100 times, we estimated to be 0.2. Okay, it wasn't that bad, but it was between 0.03 of the actual probability. It wasn't that close. The margin was large because our simulation size was small. Now, you see, if you really want to compute the probability analytically, what we get after this Monte Carlo simulation should be within 0.005 of that actual probability. It should not be. I mean, we are confident with 95% probability that it will be within 0.005. Okay, so there's nothing certain in statistics, so or everything is with some confidence. So here the expected weight, so the average weight he was catching fish was about 19.617, and standard deviation was large actually. Because of the PDF, we see that the standard deviation of the fish that is caught is large, 6, so sometimes he may catch 26 kilograms. So therefore the probability is not that small, but it's rather every approximately 1 in 5 fishing expeditions he will be catching more than 25 kilograms of fish. Okay, or 1 in 6, whatever is the 17, close to 100. Okay, so that's it. Any questions about, I think this more thorough explanation of what went on, and this assignment will help you also in your last assignment, which will be very similar to this. You will the deadline is going to be, it's going to be announced this week, probably tomorrow or maybe tonight. So it's ready, your 4th assignment, and it's very similar to this one. You will have to solve it maybe in 1 hour or 2. I mean, if you have time, I suggest you just work on it this weekend and get it over with. Okay, but the deadline is going to be, I think, July 10th or around something. Maybe July 12th. So it will cover the working on the assignment will cover your final exams weeks 2. But yeah, it will be really easy. It will not take more than an hour of your time if you just understand what we did in this assignment. It's you can just work on it this weekend, as I said, and finish it. Okay, so that will be your final assignment, and it will be similar to this one. It will not be probably Poisson. It will be some other distribution, but the rejection sampling part is going to be similar. You may reuse code from here that I shared with you. So I believe it's going to be very easy. All right. Any other questions from this? If not, this concludes the chapter 5. Okay. Now I'm going to do a small introduction to chapter 6. Since we are ahead of section the 3, that's why I spent this additional minutes on finalizing chapter 5. Since also your final assignment is about chapter 5, so it was worth to spend this additional 40 minutes on this assignment. All right, so what are stochastic processes? I will just give you some examples first without going over the slides at all. Stochastic processes are, as I said, random variables that change over time. So I will give you some examples. For example, up to now we have all talked about, for example, the fish he caught in 3 hours. What if you wanted to change this random variable? So it's when you say x is the variable, for example, the fish caught in 3 hours. It fixes this, okay? So there's nothing stochastic about this. What if you want to have a random variable which shows the fish the fisherman catches at every time interval? So, for example, he starts catching fish, okay, and you want to define a random variable to indicate at time t, when I observe this fisherman at time t, what is the number of fish he catches? If I observe him again at another time, let's call it t2, what is the number of fish this time? Okay, so we can actually define a random variable, not unlike we had in the assignment where we fix the time and say, okay, let's x be the fish that is caught in 3 hours. I just name it like this. Let x be the uh, number of fish the fisherman catches, and that's it. So what is it going to be? I will keep watching the fisherman, and I will keep watching the fisherman starting at time 0, and I will keep doing that. So my random variable x now has a second parameter, which is t. When you are going to ask what is, you will be asking questions like what is the total, what is the number of fish caught until t3, t3. Okay, so that will be the value of x here. And your random variable here has another parameter t this time. So this makes it a stochastic random variable. As you can see, it's something different. And you can guess that it will start, x is going to start 0. Okay, so at t is equal to 0, I can say x0 is 0. I'm sure of that. There is nothing stochastic about it. It's always 0. At the start of the session, the fisherman starts with 0 fish. And then the value of this x variable, as I keep watching it, I think it will going to be something like this. Let me draw a graph. Now I will have a t-axis here, which since it becomes a different parameter. And this is my x. And it will be something like this. So if this is 1, 2, 3, and 4, 5, I couldn't draw it very nicely, but what I'm seeing here is that the number of fish he catches is always something increasing, and it's increasing at arbitrary time intervals. So sometimes you have to wait a lot to catch the next fish. Sometimes you don't need to wait a lot. From after he catches the 5th fish, he just waited like maybe a couple of minutes, if this t is in minutes, to catch the 6th fish. But such a process is called a counting process. We are counting. So this random variable that we are observing is actually stochastic, and it changes over time. As time increases, the value x changes. Okay, so in a counting process like this, we have this is a continuous time. The time that elapsed is like an exponential distribution. It's continuous. We have continuous time, and what we're counting, the variable itself, the x itself, is something discrete. It's not, he cannot catch half a fish or 0.3 of a fish. He will catch whole fishes. So x is coming from the integer domain. Therefore, the variable, its value itself is discrete. So we call the when we are monitoring a variable x like this, which is discrete, we call those actually states. We don't name the values of those variables as the random variable's value. We call it state. So it's like we jumped from state 5. So it was x was at state 5. Its state, which means that x currently, the current variable at this point was 5. And then it jumped to state 6 after it changed to state 6 after the fisherman caught a fish. Okay, so therefore these states are called discrete states. It's a discrete state, continuous time stochastic process. We are going to focus on in most of this chapter, we are going to focus on discrete state and discrete time. How can time be discrete? Let's, for example, instead of such a process in which time is continuous is actually called Poisson process. We are going to talk about this, specifically Poisson process. There is another counting process which is called binomial process. Okay, now let me describe another random variable. the number of baskets you make in free throws. So you're going to make some free throws, maybe 100 free throws at the end, okay? But you keep making free throws. Now, look at the time axis. The time axis now is discrete. Your first throw, second throw, third throw, fourth throw. It's not time anymore. It's the trials, okay? Eighth throw, ninth throw, 10. Actually, 100 is not here. It's going to go all the way 100. But imagine you're making free throws, and x is a variable that shows the number of free throws made. Okay, so it will start at 0. If you make your first free throw, it will jump to 1 here at 1. So it will, if you make your second throw, it will also jump to 3. But if you don't make a couple free throws, 5, if you miss 5 consecutive free throws, x is going to stay at 2. But if you make your 7th throw again, it's going to jump to 3. So 1, 2, 3. So the states, when you're counting things, when the state is discrete, and here we are throwing basketball and a certain number of times. It's also a number, a count. The time itself is also discrete, so it becomes a discrete state, discrete time random process. For example, if you're measuring, do we have continuous, for example, continuous state and continuous time random variables? For example, CPU usage. If you're monitoring your CPU usage, okay, over time, if you, for example, open the performance monitor app. Let's see, what kind of an app is this? Yeah, look at this. What is this? Is this the processor information? Yeah. See what is going on here? This is what we're watching here at the moment is a continuous state, because the CPU usage is something, a real number, a percentage between 0 and 100, okay? And therefore it's continuous. This is the state, the y-axis is the state, it's continuous. And the time itself, although it's at increments of seconds maybe, so it's updated every second, since seconds are like continuous, I mean, when you get to the bottom of it, everything is discrete. I mean, we cannot go infinite precision, but when you're measuring seconds, they become, I mean, the time in seconds, as we have seen in exponential before, it's a continuous process. It's not trials, number of trials, it's continuous time that is flowing. And since the percentage of the CPU percentage usage is also some real number between 0 and 100, this is also continuous. So what we're watching here is that random variable x that shows, which is a stochastic process, how long the CPU will be used at a certain time, and how much amount, what is the percentage of CPU. So stochastic processes are like this. We are going to have a new parameter in our variable, which is this t that we have. And we are going to see different things about those. Especially we are going to learn something that is called a Markov process. Or not with W, with V, Markov process, in which where the state is going to go next is going to be determined only by the previous time point. So a Markov process will be a discrete time process. We are going to have time points which are discrete, and what will happen next will only be determined by what is present. The probability only depends on present. If it's like that, not all processes are Markov processes, but we're going to focus on these. I'm going to talk about and give some examples too. So let's have a 10-minute break now. I will stop recording.